Hello everyone, I am Yuqi Xue from UIUC. In this talk, I will present IceClave, a trusted execution environment for in-storage computing. So nowadays, we have got used to host-based computing, where we move data from the SSD to the host and then perform computation on the host. However, as we increase the size of the data, I/O becomes a bottleneck. So we developed the technique called in-storage computing, where we offload computation to the SSD to alleviate this I/O bottleneck. And we also further exploit the internal flash bandwidth to speed up data processing. So to facilitate in-storage computing, many frameworks have been developed. For example, Biscuit proposes a flow-based programming model for in-storage workloads. Willow develops a lightweight in-storage operating system. Also in industry, Samsung integrates FPGA accelerators into the SSD. However, most of the existing frameworks focus on performance and programmability, but few of them consider security as a priority. Now, this brings us a lot of security problems for in-storage computing. For example, when we offload multiple applications to the SSD, if one of them contains malicious code, this malicious application can attack co-located applications or attack the flash translation layer. Even worse, a malicious cloud platform operator which has physical access to the device may conduct physical attacks, such as spot snooping or man-in-the-middle attacks against the user data. All these attacks may cause data leakage or even data loss. So to prevent this from happening, it is desirable to build a secure in-storage computing environment. Now, to overcome these security threats, there are some existing techniques such as Intel SGX and ARM TrustZone. However, SGX is not available in modern SSDs. And although ARM TrustZone may be supported by the SSD controllers, which are typically ARM processors, it is still unclear how to apply TrustZone to in-storage computing. Also, both of them cannot protect against all types of attacks faced by in-storage computing, and they also suffer from significant performance overhead that are not affordable by the SSD controllers. So this motivated us to design and build IceClave, which is a trusted execution environment specialized for in-storage computing. IceClave protects the FDL from malicious in-storage applications. It enforces security isolation between different applications, and it also secures user data against physical attacks. So before we dive into the design details of IceClave, let us first define the threat model. As we have just mentioned, a malicious in-storage application can attack co-located application and the FDL. Also, a malicious cloud platform operator may conduct physical attacks. Similar to Intel SGX, we assume that the processor chip is secure against physical attacks. We also assume that the host runtime and host to SSD offloading channel is secure, because orthogonal techniques such as TEE on host and secure RPC are already available in modern cloud platforms. So keeping the threat model in mind, I will explain how IceClave is designed to prevent all these attacks. First, IceClave protects the FDL from malicious in-storage applications. This can be done by placing the FDL in the secure world, which is isolated by the ARM TrustZone hardware. However, this may incur significant performance overhead because when an application wants to access flash memory, it needs to context switch to the secure world to invoke the FDL. To address this problem, we move the address mapping table to the protected memory region in the normal world, and we enforce that the address mapping table is read-only to the in-storage applications. This protects the FDL with low performance overhead. Second, IceClave enforces security isolation between different applications. This is done by memory isolation in the off-chip DRAM and also enforcing access control to the flash memory. When an application accesses data in the DRAM, IceClave leverages ARM processor's memory management unit to provide page-level isolation. When an application accesses flash memory, IceClave enforces flash access control by checking the permission bits in the address mapping table. Third, IceClave also secures data against physical attacks. This can be done by protecting data in the off-chip DRAM against physical attacks using Merkle tree and split counter for memory encryption and integrity verification. Our insight is that in-storage applications are mostly read-intensive, but existing split counter design may incur significant performance overhead because split counter is optimized for write performance. Based on this insight, we propose a hybrid counter design, which optimize for memory read performance by removing redundant minor counters from the split counter design and packing more major counters to improve counter fetching locality. So putting this all together, IceClave introduces new hardware components to mitigate physical attacks and secure user data. It also includes software runtime to enforce security isolation between applications and the FTO. We implemented IceClave on FPGA and evaluated IceClave with simulators. We run data-intensive workloads that are typical for in-storage computing. On average, IceClave introduces only 7.6% of overhead compared to in-storage computing without security. To summarize, IceClave is the first trusted execution environment for in-storage computing. It is faster than host-based computing while providing strong security. Thank you for listening.